In algebra, the discriminant of a polynomial is a function of its coefficients, typically denoted by a capital D or the capital Greek letter delta. It gives information about the nature of its roots. For example, the discriminant of the quadratic polynomial is. Here for real a, b and c, if I0, the polynomial has two real roots, if I equals 0, the polynomial has one real double root, and if I0, the polynomial has no real roots. The discriminant of the cubic polynomial is. For higher degrees, the discriminant is always a polynomial function of the coefficients. It becomes significantly longer for the higher degrees. The discriminant of a general quartic has 16 terms, that of a quintic has 59 terms, that of a sixth-degree polynomial has 246 terms, and the number of terms increases exponentially with the degree. A polynomial has a multiple root in the complex numbers if and only if its discriminant is 0. The concept also applies if the polynomial has coefficients in a field which is not contained in the complex numbers. In this case, the discriminant vanishes if and only if the polynomial has a multiple root in its splitting field. As the discriminant is a polynomial function of the coefficients, it is defined as soon as the coefficients belong to an integral domain R and, in this case, the discriminant is in R. In particular, the discriminant of a polynomial with integer coefficients is always an integer. This property is widely used in number theory. The term discriminant was coined in 1851 by the British mathematician James Joseph Sylvester. Definition: in terms of the roots, the discriminant is given by where is the leading coefficient and are the roots of the polynomial in some splitting field. It is the square of the van der Moen polynomial times. As the discriminant is a symmetric function in the roots, it can also be expressed in terms of the coefficients of the polynomial, since the coefficients are the elementary symmetric polynomials in the roots. Such a formula is given below. Expressing the discriminant in terms of the roots makes its key property clear, namely that it vanishes if and only if there is a repeated root, but does not allow it to be calculated without factoring a polynomial, after which the information it provides is redundant. Hence the formula in terms of the coefficients allows the nature of the roots to be determined without factoring the polynomial. Formulas for low degrees: the quadratic polynomial has discriminant. The cubic polynomial has discriminant. The quartic polynomial has discriminant. These are homogeneous polynomials in the coefficients, respectively of degree 2, 4 and 6. They are also homogeneous in term of the roots, of respective degrees 2, 6 and 12. Simpler polynomials have simpler expressions for their discriminants. For example, the monic quadratic polynomial x2 plus bx plus c has discriminant I equals b2 or 4c. The monic cubic polynomial without quadratic term x3 plus px plus q has discriminant I equals a 4p3 or 27q2. In terms of the roots, these discriminants are homogeneous polynomials of respective degree 2 and 6. Homogeneity: the discriminant is a homogeneous polynomial in the coefficients. For monic polynomials, it is a homogeneous polynomial in the roots. In the coefficients, the discriminant is homogeneous of degree 2 and R2. This can be seen two ways. In terms of the roots and leading term formula, multiplying all the coefficients by I does not change the roots, but multiplies the leading term by I. In terms of the formula as a determinant of AA, 2 nar1, matrix divided by an, the determinant of the matrix is homogeneous of degree 2 nar1 in the entries, and dividing by an makes the degree 2 nar2. Explicitly, multiplying the coefficients by I multiplies all entries of the matrix by I, hence multiplies the determinant by I2 nar1. For a monic polynomial, the discriminant is a polynomial in the roots alone, and is of degree n, nar1, in the roots, as there are terms in the product, each squared. Let us consider the polynomial. It follows from what precedes that its discriminant is homogeneous of degree 2 nar2 and the end quasi-homogeneous of weight n, nar1, if each is given the weight I. In other words, every monomial appearing in the discriminant satisfies the two equations. And These thus correspond to the partitions of n, now 1, into it 2 now 2 parts of size at most n. This restricts the possible terms in the discriminant. For the quadratic polynomial there are only two possibilities for either 1, 0, 1, or 0, 2, 0, given the two monomials a and b2. For the cubic polynomial, these are the partitions of 6 into 4 parts of size at most 3. All these 5 monomials occur effectively in the discriminant. While this approach gives the possible terms, it does not determine the coefficients. Moreover, in general not all possible terms will occur in the discriminant. The first example is for the quartic polynomial, in which case satisfies and, even though the corresponding discriminant does not involve the monomial. Quadratic formula, the quadratic polynomial has discriminant, which is the quantity under the square root sign in the quadratic formula. For real numbers a, b, c, one has, when I0, p, x, has two distinct real roots. And its graph crosses the x-axis twice. When I equals 0, p, x, has two coincident real roots. And its graph is tangent to the x-axis. When I0, p, x, has no real roots, and its graph lies strictly above or below the x-axis. The polynomial has two distinct complex roots. An alternative way to understand the discriminant of a quadratic is to use the characterization as 0 if and only if the polynomial has a repeated root. In that case the polynomial is the coefficients then satisfy so and a monic quadratic has a repeated root if and only if this is the case, in which case the root is putting both terms on one side and including a leading coefficient yields, discriminant of a polynomial. To find the formula for the discriminant of a polynomial in terms of its coefficients, it is easiest to introduce the resultant. Just as the discriminant of a single polynomial is the product of the square of the differences between distinct roots, the resultant of two polynomials is the product of the differences between their roots, and just as the discriminant vanishes if and only if the polynomial has a repeated root, the resultant vanishes if and only if the two polynomials share a root. Since a polynomial has a repeated root if and only if it shares a root with its derivative, the discriminant and the resultant both have the property that they vanish if and only if p has a repeated root, and they have almost the same degree and thus are equal up to a factor of degree 1. The benefit of the resultant is that it can be computed as a determinant, namely as the determinant of the Sylvester matrix, or 2 null AA1 matrix, whose null AA1 first rows contain the coefficients of p and the n last ones the coefficients of its derivative. The resultant of the general polynomial is, up to a factor, equal to the determinant of the 2 null AA1 Sylvester matrix. The discriminant of is now given by the formula. For example, in the case n equals 4, the above determinant is. The discriminant of the degree 4 polynomial is then obtained from this determinant upon dividing by. In terms of the roots, the discriminant is equal to, where a1, Rn are the complex roots of the polynomial. This second expression makes it clear that p has a multiple root if and only if the discriminant is 0. The discriminant can be defined for polynomials over arbitrary fields, in exactly the same fashion as above. The product formula involving the roots remains valid. The roots have to be taken in some splitting field of the polynomial. The discriminant can even be defined for polynomials over any commutative ring. However, if the ring is not an integral domain, above division of the resultant by should be replaced by substituting by 1 in the first column of the matrix. Nature of the roots. The discriminant gives additional information on the nature of the roots beyond simply whether there are any repeated roots. It also gives information on whether the roots are real or complex, and rational or irrational. More formally, it gives information on whether the roots are in the field over which the polynomial is defined, or are in an extension field, and hence whether the polynomial factors over the field of coefficients. This is most transparent and easily stated for quadratic and cubic polynomials. For polynomials of degree 4 or higher this is more difficult to state. Quadratic, because the quadratic formula expressed the roots of a quadratic polynomial as a rational function in terms of the square root of the discriminant, the roots of a quadratic polynomial are in the same field as the coefficients if and only if the discriminant is a square and the field of coefficients. In other words, the polynomial factors over the field of coefficients if and only if the discriminant is a square. As a real number has real square roots if and only if it is non-negative, and these roots are distinct if and only if it is positive, the sign of the discriminant allows a complete description of the nature of the roots of a quadratic polynomial with real coefficients, I0, two distinct real roots, factors over the reals. I0, two distinct complex roots, does not factor over the reals. I equals 0, one real root with multiplicity 2, factors over the reals as a square. Further, for a quadratic polynomial with rational coefficients, it factors over the rationals if and only if the discriminant euro, which is necessarily a rational number, being a polynomial and the coefficients euro is in fact a square. Cubic. For a cubic polynomial with real coefficients, the discriminant reflects the nature of the roots as follows. I0, the equation has three distinct real roots. I0, the equation has one real root and two complex conjugate roots. I equals 0, at least two roots coincide, and they are all real. It may be that the equation has a double real root and another distinct single real root. Alternatively, all three roots coincide yielding a triple real root. If a cubic polynomial has a triple root, it is a root of his derivative and of his second derivative, which is linear. Thus to decide if a cubic polynomial has a triple root or not, one may compute the root of the second derivative and look if it is a root of the cubic and of his derivative. Higher degrees, more generally, for a polynomial of degree n with real coefficients, we have I0, for some integer k such that, there are 2k pairs of complex conjugate roots and n 4k real roots, all different. I0, for some integer k such that, there are 2k plus 1 pairs of complex conjugate roots and n 4k 2 real roots, all different. I equals 0, at least two roots coincide, which may be either real or not real. Discriminant of a polynomial over a commutative ring. The definition of the discriminant of a polynomial in terms of the resultant may easily be extended to polynomials whose coefficients belong to any commutative ring. However, as the division is not always defined in such a ring, instead of dividing the determinant by the leading coefficient, one substitutes the leading coefficient by 1 in the first column of the determinant. This generalized discriminant has the following property which is fundamental in algebraic geometry. Let f be a polynomial with coefficients in a commutative ring A and E its discriminant. Let I be a ring homomorphism of A into a field K and I, f, be the polynomial over K obtained by replacing the coefficients of f by their images by I. Then I, d, equals 0 if and only if either the difference of the degrees of f and I, f, is at least 2 or I, f, has a multiple root in an algebraic closure of K. The first case may be interpreted by saying that I, f, has a multiple root at infinity. The typical situation where this property is applied is when A is a polynomial ring over a field K and I is the substitution of the indeterminates in A by elements of a field extension K of K. For example, let f be a bivariate polynomial in X and Y with real coefficients, such that f equals 0 is the implicit equation of a plane algebraic curve. Viewing f as a univariate polynomial in Y with coefficients depending on X, then the discriminant is a polynomial in X whose roots are the X coordinates of the singular points, of the points with a tangent parallel to the Y-axis and of some of the asymptotes parallel to the Y-axis. In other words, the computation of the roots of the Y discriminant and the X discriminant allows to compute all remarkable points of the curve, except the inflection points. Generalizations. The concept of discriminant has been generalized to other algebraic structures besides polynomials of one variable, including conic sections, quadratic forms, and algebraic number fields. Discriminants in algebraic number theory are closely related, and contain information about ramification. In fact, the more geometric types of ramification are also related to more abstract types of discriminant, making this a central algebraic idea in many applications. Discriminant of a conic section. for a conic section defined in plane geometry by the real polynomial. The discriminant is equal to and determines the shape of the conic section. If the discriminant is less than 0, the equation is of an ellipse or a circle. If the discriminant equals 0, the equation is that of a parabola. If the discriminant is greater than 0, the equation is that of a hyperbola. This formula will not work for degenerate cases. Discriminant of a quadratic form, there is a substantive generalization to quadratic forms Q over any field K of characteristic L 2. For characteristic 2, the corresponding invariant is the half invariant. Given a quadratic form Q, the discriminant or determinant is the determinant of a symmetric matrix S for Q. Change of variables by a matrix A changes the matrix of the symmetric form by which has determinants, so under change of variables, the discriminant changes by a non-zero square, and thus the class of the discriminant is well defined in K/K2, that is, up to non-zero squares. See also quadratic residue. Less intrinsically, by a theorem of Jacobi, quadratic forms on can be expressed, after a linear change of variables, in diagonal form as. More precisely, a quadratic forms on V may be expressed as a sum, where the Lie are independent linear forms and n is the number of the variables. Then the discriminant is the product of the I, which is well defined as a class in K/K2. For K equals R, the real numbers, 2 is the positive real numbers, and thus the quotient R/R2 has 3 elements, positive, 0, and negative. This is a cruder invariant than signature, where NO is the number zeros and R plus or minus is the number of A plus or minus ones in diagonal form. The discriminant is then 0 if the form is degenerate, and otherwise it is the parity of the number of negative coefficients. For K equals C, the complex numbers, 2 is the non-zero complex numbers, and thus the quotient C/C2 has 2 elements, non-zero and 0. This definition generalizes the discriminant of a quadratic polynomial, as the polynomial homogenizes to the quadratic form which has symmetric matrix, whose determinant is up to a factor of 4. This is, the invariance of the class of the discriminant of a real form corresponds to the corresponding conic section being an ellipse, parabola, or hyperbola. Discriminant of an algebraic number field. Alternating polynomials. The discriminant is a symmetric polynomial in the roots. If one adjoins a square root of it to the ring of symmetric polynomials in n variables, one obtains the ring of alternating polynomials, which is thus a quadratic extension of. References. External links, MathWorld article, PlanetMath article.